Okay. So, I think in the next two lectures, what I'm going to do is phase transitions and gravitational waves from that. So, to cover this, I have to start with what's an effective potential, then how that effective potential changes with temperature, and then phase transitions and how gravitational waves are emitted. So that's what I'll do in the next two lectures of this today and tomorrow. And I had an incomplete discussion about this pulsar, which I think in today's lecture is already 10 pages notes, so I'll not do it now. But I'll give you a reference where you can read it up, some lecture notes. So this is for pulsar timing. And this is 2-point correlations. So this is what was that Helling's Downs curve. And this you can look up in the lecture notes. Yokoyama. Okay. So with the background I gave you about stochastics, I think you will be able to follow that derivation. Okay, so today I'm going to start with effective potential. And I'll do the zero temperature part today and then maybe thermal part next. So normally we are used to this idea, we know effective field theories. So the idea here is that supposing you have experiments which are probing some energy, and let's say you have a LHC which probes 10 TeV. Then write theory, integrate out particles with mass greater than E. Okay, which means that these particles do not appear as external legs, they only appear in the loops. Okay, and then write the theory of the lighter particles. Okay, so what is the effective theory? Theory of particles with Mi greater less than E, which will be produced as external legs. So for instance, for Higgs, let's say, I want to write the Higgs effective theory. It look like, so Higgs is a doublet, and it will look like something like mu square h dot h dagger. So it's a SU2 doublet, so you have to form a SU2 singlets from this. So you have to have a h dagger. And you can have C1 so what you are doing here is you are writing the theory for Higgs, where you have here, let's say, 4 Higgs, and you are integrating out these particles, heavy particles, they are in the loop. Okay, so that's this term. Similarly, this term would be 6 Higgs particles. Similarly, like that. Yeah, so lambda by 4, there is a tree level term. Then you generate things in the loops. So this is combination of lot of things. Okay. So the loops will generate the quartic interaction, then 6 particle interaction and so on. So then you say that in a collider, this is the thing we test, that we have a Higgs and Higgs which are in the external legs and the internal particles we don't see, and we have to use a theory where this is your effective theory. Okay, so that's what's the usual effective field theory, which is used in high energy context. But there's another sense in which we have an effective theory, and this is the infrared effective theory, and this is what's called the effective potential. And a good example of this is, I'll give you an example, and then that you have that, let's say you have, so you have a lambda phi to the 4 theory, okay. Add to that, so this is, let's say, n vertices. N equal to, so 1 is already covered here, 2 onwards. So n is the vertices. So you see these are quartic vertices with lambda at each place. Okay. And calculate what this potential is. And this is what's called Coleman Weinberg potential. So this will be one loop at all orders in coupling. And so the loop particle need not be just this particle, it can be any particle with which where phi interacts with it. So supposing you have a fermion, let's say you have a so this is a Yukawa coupling, right? So its effective mass would be a field dependent quantity plus y times phi. So the mass will depend upon the value of the field. Okay, and now you can imagine a loop of fermion. So this is your F and this is your phi. And take this n vertices and sum over n again from 2 to. Okay, so you'll get an object where you have integrated out the fermion and it's just a function of the phi. So that's the same Coleman-Weinberg potential with contributions from the fermions. Similarly, you will have contributions from gauge bosons and so on. So every particle which interacts with phi should be put in the loop, and only the phi in the external leg should be there, and you compute this one loop at all orders. Now here use so, and all orders in lambda. You can have infinite legs. So 1, 2, like 2, you sum over all. And this is a little bit of cumbersome process to do with Feynman diagrams, which is why I'll use a different method. I'll use something called the background field method, which is very simple to do then. Okay. And here, what is different, the main difference is that this is applied, so in the end you want a V phi, and you want this V phi at, let's say, cosmological scales, which means that you want the x dependence not to be there. So there is no x dependence. So there is, which means in the, or a better way to put it is, spatial derivatives of the field will treat them to be 0, which means we are talking about constant fields. So this has application in cosmology, the phase transitions and inflation and so on. And clearly, see, this is K. So we are talking about Ki in the 0 limit. So we are talking about this thing we are probing in the infrared limit. Okay. So for that, the particle in the loops is, so we will take all particles in the loop. Momentum is 0. If the gradient is 0, that means the momenta in the the spatial momenta is 0. Okay. Yeah. Del I is in the Fourier space is Ki. Okay. What? No, so what we normally have is we keep the del T phi, and this T changes in the cosmological scales, not in the particle physics scales. So this T is proportional to H inverse. So it will change with the expansion of the universe. Okay. So, but that energy or this eigenvalue of this dt is still very small compared to any of the masses. Yeah. No. So you are talking about a propagating field. I am talking about a homogeneous field. Universe expands or cools down, and everywhere the field goes up and down simultaneously. There is no propagation. Okay. So why is not widely? But you are not sending any information from one side. The universe is expanding and each place is coming down separately together. They are not communicating. So, No, it's not an assumption. You can have perturbations of this and do useful things there. But I am saying the first thing what we are calculating is what is the constant field which is coming out. What is the constant potential which is coming out due to all the particles. So that's what we are calculating. I'm not saying the real world it has to be like that. So you have a constant field, then you have a perturbations. Okay, those perturbations will then del I will be, phi will not be 0. There will be some gradients and there will be local Newtonian potential. But the first order we calculate just the constant field which is just changing in time. Okay. So, yeah, so now, no, at all distances. So the infrared K equal to 0.
All particles in the loops, because you are assuming that this is valid for at all scales.
All scales, yeah. So now we are taking all particles. All particles in the loop. But it will so turn, so not just the particles are heavier than the particular scale to get the effective theory. Here you have to take all particles which couple with the phi, but it will so turn out that the particles which have the largest coupling will give you the most contribution. Okay. So for instance, the fermion with the largest coupling will give you the, so for the Higgs, the top loop will be, will contribute to this Coleman potential most. But that's the opposite of what happens in a normal loop. The heaviest particle contributes least. Okay. So in that sense, this calculation throws up a different answer than this normal series of one loop, two loop and so on. Okay. Yeah. So this is sum over all diagrams where you have n vertices. So the first term is lambda by 5. So I should write like that. So this will give me lambda 5 to the 4. This will make me VCW. I will calculate this. I will tell you what this gives. So the first term is this one. The second term doesn't look like this at all. Okay. Okay, so a scalar field has a classical background. A fermion field, there is no sense. Basically, it has to do with the fact that you have a large number of occupation. So this can be written for bosonic fields. And in cosmology, it's useful to just take a scalar field. But I can imagine this being done for a magnetic field. Okay, so you can do this for a magnetic field. So you can do for all bosonic fields this kind of thing. Okay. All right, so the method I'm going to use okay, so this is the object. Calculate if there is a basic coupling like that, then imagine objects of diagrams of this, calculate the total contribution, what is the Lagrangian. Okay. So I'll use instead of the Feynman diagrams, I'll use what's called the background field method, or this path integral method. Actually, it's simpler, you'll see. It's also called the background field method. So let's start with a Lagrangian. Where this V phi can have mass term plus this kind of thing. Okay. Now break up this one into, write V phi as V phi background. So this is the constant field whose potential we are trying to calculate, the phi b. And sorry, not V phi. First let me just write the phi as phi background plus a quantum fluctuation. And what I am going to do, so that internal line there is my quantum fluctuation which I am integrating out to get an effective theory of the background field. Okay. So what I will do now is, so I have to integrate out to get the effective V phi b, which will be different from the original. Okay. So okay, so what we do is we write this phi and put it back in the Lagrangian and keep different zeroth order in phi. This will be just my Lagrangian of phi b, which is minus half phi b box phi b minus v of phi b. So this is my classical Lagrangian with the background. Okay. First order. Yeah. Yeah. How can I use the? Well, here normally what happens is, if your field, the masses, okay, the field vary over R, which is 1 upon m phi. Okay. If your metric can be thought as flat over this distance. So here we are assuming that gravity doesn't play a role at these short distances, inverse masses. And so what we will do is we will write this effective thing, and we will then calculate the T mu nu of this phi b, and then calculate how much is the gravitational curvature from this T mu nu. Okay. What? Well, if the masses are, he's saying that why don't you take the curved space in this box if you are applying it to the early universe. So what we are saying is, this is, if you have a truly curved space calculation, like for instance if you have a inflation for instance, then you have to use the de Sitter metric as a background. Okay, because this is a strong curvature. But for the normal operations, like you have a TV potential, there the background can be thought of as flat. So basically, if the background doesn't change, the curve over the inverse mass of the particle, then you can treat it as a flat space for this calculation. Okay, and then you put it in the T mu nu and calculate the background after that. Okay, so here what I have done is I have just put this in the potential in the Lagrangian and just collecting order by order. So here you will have, so this will be 0, L1 will be, this will be a function of phi and phi by, this will be minus half phi b box phi So I just, that will have one order in, sorry, this is just it should be this curly phi, which is the fluctuation. So you could have this fluctuation here, or you can have this here, only one phi and one phi b. Okay, and either way you can integrate by parts and put the box on the phi, because this one is a constant, as I said. Okay, why phi? Because you write this potential in terms of phi and then take the Taylor expansion. So first order is phi prime this, right? But this thing is 0 because that's the equation of motion for the background. If you, okay, sorry, this should have been put a phi here and a phi background on this. This is the equation of motion for the background. Okay, so assume that phi b obeys the classical so the first order term is 0, okay, and this is curly phi. I am taking variation with respect to small phi, but yeah, so basically what I am doing is delta s upon delta phi times this is phi, but this object is the equation of motion for your classical field. So this is object is 0. That's what you see clearly. Okay. So we are taking variation with respect to the full field and evaluating it at phi equal to phi b and then multiply by the extra del. Okay. So this is 0 and then we'll get a quadratic term where there are two phi's. So again, this is by Taylor expanding the potential to second order. Fine. All right. So we have this. Then I'll write my So this is my effective action for phi b. This I will define as, okay, integrate out d phi, the fluctuation. So please be careful about the small phi and the capital phi is the full field, phi b is the background, and this var phi is the fluctuation. So this will be I plus minus whatever plus, okay. So from the total action, integrate out the fluctuation. You will be left with something which is just a function of the background. Call that the effective potential, effective action. Okay. All right. So, this guy can write one more line here. This will, if you write this, okay, you have a contribution 0 and second term. This term will not contribute. So, the 0th term has nothing in small phi. So, you can take it out of the path integral. So, it is minus I s of phi b. So, the action of the background plus, multiplied by d of phi, this is the path integral, e to the power phi box phi One second. What? More? L? Yeah, but you can integrate by parts and make this operate on phi b, and then the same equation of motion gets. So this will work for phi b here or here, the same. Okay, the second term will be, the phi b will be here and phi will be here, right? Huh? Half? No, it will be there, it is the same. You can check. So basically, and you can integrate by parts, but because this Lagrange is inside a volume. Okay, so then, so here what you do is, go to Euclidean space and you write this as, so we want to calculate this object. So whatever we get from this object, we'll add to my classical action, and that will be what I will call the one loop action, because I am just integrating out d phi once. So this will give me one loop. Okay. So you can see that this is a quadratic in phi and you are integrating over phi. So what I'll do is, I'll use this expression which we know and just apply it blindly into the field theory context. So the expression that I know is dx pi I, or let me just write in the single this thing, half x ax is root pi upon A, and if you make this a matrix Ij, so I'll write this clearly, Xi, Aij, Xj. So this is a column row matrix, and you integrate over all the components of this Xi. What you will get here is the determinant of this A. Okay. And to see that, basically what you do is take this, diagonalize this matrix, write it as sum of the eigenvalues, and you will see that what you will get is product of the eigenvalues. Okay. For each exponential you will get an eigenvalue of A, and that will give you 1 by square root of that eigenvalue. Product of the eigenvalues will be give you the determinant. Okay. Now I use this blindly. So what I am going to do, I am going to take dt to I d tau with a plus or minus, so that you will get basically d phi minus phi let me write this clearly. So we are going to calculate this object. Okay. So this looks like xx with the operator here. Okay. So there is phi and the operator in the middle, quadratic, and this summation over ij indices, this is just this d4x, because here instead of the x I, you will have phi of x, which is summed over. Okay. So this will then give you of the operator itself. And we'll see what this means. Plus multiplied by some constant which I'll double prime is yeah. So this is the thing I'm going to use. Now what is this? I'll keep that here. So how do I deal with this? Use this relation. Determinant of an operator is e to the trace log a. Okay. And how do you prove this? Again, take this in the diagonal form. Okay. So diagonal form, diagonals will be the eigenvalues, lambda 1, lambda 2, etc. So log of trace log a means sum of the eigenvalues, which means exponential of lambda 1 multiplied by exponential of log lambda 2 and so on. So this will give you basically lambda 1, lambda 2, you can, which will be just the determinant. Okay. So it's easy to see. So I use that here, and then what I get is 1 upon determinant of this operator box plus v double prime. So using this will give me e to the power minus half trace log box plus minus half, because this is determinant of minus half. Okay, so I am using that in this one. Fine? Okay. So now to calculate that, so I'll start with this minus half trace log box plus V prime. Okay. Trace means you have to trace out all the, as I said, here the trace was volume integral. Okay. So this is actually minus half d4x, okay, log box plus V double prime. Okay. And to calculate this, since the eigenvalues of the box operators are in the momentum space, this is the momentum operator square, so you go into momentum space. So this will be minus half d4x d4k upon. So you have to sandwich and this kx is just e to the power I kx. These things cancel. You can write the unit operator as kk integrated over k, and you finally will get this. Okay. So this and this cancel out, and what you are going to be left with is minus half d4x d4k log because that box is minus k square in the k space. Okay, and Vb is a constant, V double prime is a constant, it is just a function of phi b. Right? Okay. So now the thing is, how do you calculate this? Again, go to the so here basically what you are going to do is k0 k will go to ik0 k okay, and then my k square, this k square which was k0 square minus k square will go to and I will call it minus k Euclidean square. Okay. So I will get basically in the Euclidean space this object will be this object we are calculating, this will be minus half d4x so here this is Euclidean k also. Okay. And what were we calculating? We were calculating this exponential, that extra exponential. So what we have is finally e to the power I effective action in phi b is e to the minus the classical thing plus in the exponent I have e to the power minus half d4x and k. So sometimes it is written as k square plus m square also, because v double prime is basically m effective. You can also write as m square effective. Okay. So I can, okay. So then, what does this tell you? You have calculated something which is a, so this was I, okay. This is my effective potential, okay, extra potential which comes from integrating out my small phi, the fluctuating field, okay. So this is this is V1, one loop phi b, okay. So so again, to compare with the previous term, I go back to the standard Minkowski. So here this dxi I will put back a I, okay, because I want to just add this to the previous action. I had gone to Euclidean just to evaluate that, but I come back to it. So basically then my extra field so what this gives me is that V effective is V zeroth order of phi b, which is sitting inside this one, this guy, and I get a one loop plus half, and this will be d4k. So this k was still Euclidean. I will keep it like that because that is easier to calculate. And I will call it k square plus m effective square, or sometimes just write m because effective is too tedious to write all the time. Okay. So this is my effective one loop potential. The same thing, but I don't want to write again. Okay. So now the thing is, how do we evaluate it? Yeah? One loop because we integrated out d phi 1. So if the number of times we integrate out, that is the number of loops which are there. What? Phi which one? Yeah. Yes. Because, so what we did was, we are calculating this object where we have a phi b here and a small phi which has been integrated out. Okay. So this is in the loop. It's no longer there in the action. Okay. So this is coming from the effect of that small phi in the loop. Okay. So we are calculating this object with phi b. So this is a potential V1 of phi b. And that's this. Okay. Okay. So now I will actually calculate this. And this is a tedious calculation, so please bear with me. How much time I have?
25 minutes.
Huh?
20 minutes.
20 minutes. Okay, I think I can finish. Okay, so I will calculate this using, this is a very long calculation, so I need a lot of, what? Yeah, it will diverge. So that is the whole story now I am telling. That it will be a divergent term and how you cancel the divergences and get a finite thing out of it. So that's the long calculation part. I mean, how to isolate the divergence. So we are calculating V1 phi half, okay, D4P or this K here, okay. This is divergence, so I am using what's called dimensional regularization. Regularize. So what I'll do is, I'll go, instead of 4, I'll go to this n dimension where n is slightly less than 4 dimension. And in the end I will take epsilon going to 0, okay, and I'll have some pole terms which I will absorb in the counter terms, and I'll get some log terms which will be there here. Okay, so let me explain that story. Okay, so if you go to n dimension, then V1 phi is half dn p okay. So since you have gone down in the dimension, you have to make it up by introducing a mass parameter mu square so this will be mu square 2 minus n by 2 okay, to compensate for the fact that you have gone away from this, okay, to keep your potential in the 4 dimensions. So the potential should be a 4-dimensional object, so I have gone away from this 4 dimension in this P integral. So I compensate by putting a mass parameter. So, okay, so that the total thing is 4 dimension. Okay. Now I use, okay. So first what I do is I calculate first V prime, which is defined now as dV1 by d. Take the derivative with respect to m square. So this is my one loop, and this phi b actually. Take the derivative with respect to m square. So that makes it puts the potential in a simpler form. This is half mu square 2 minus mu by 2 dnp So since there was a log derivative with respect to m square, we'll just give you 1 by that. Okay. And to calculate this, I will not do it from first principle. I'll just use the general expression that dnp of p square alpha divided by p square plus m square beta. This is all for Euclidean space. Okay, n-dimensional Euclidean space. This is a vector in the Euclidean space. Okay, then this is so this is the general expression for integral of this kind of object, and you can look up these derivations in Ryder or some other book. You can prove this from first principle. And I'm just going to apply it for our case. So this expression for our case means that in our case we have alpha equal to 0 and beta equal to 1. Right? Nothing in the numerator and denominator, there is only 1 power of p square plus m square. So I just use the right hand side. So my dv at d m square is half mu square and okay. So this gamma n by 2 cancels. Gamma 1 is 1. So the only non-trivial object left here is this gamma 1 minus n, which we'll calculate. So gamma of negative integers is a pole, it diverges. So you can see this n being 4. This is, when epsilon goes to 0, it becomes a gamma of a negative integer. So this will give you some non-trivial thing. Okay, and okay, this is a tedious calculation, but I'll do it in detail because this is the most difficult part of this story. So I'll, which will, okay. So I won't, so that one I'll write it as v prime. With some simplification, it becomes 1 by 32 pi square so after a few simplification steps, I'm telling you, you can massage this to gamma 1 minus n by 2. So what you do is, so because what I wanted to calculate, okay, I have to multiply another 1 upon 2 pi to the n here. Because this formula didn't have this 2 pi to the n, which we have in our, so I included that. Now in this n can be taken as 4 because constants, there is no, I mean, take the epsilon to 0, it doesn't do anything. So with all these, I take sum of those 2 pi here, and one I kept it here because I want this combination, you'll see why. But that thing all becomes like this, and if I want v, then I integrate this and I'll get 1 by Okay, we integrated with respect to m square, so that just adds a power of m square n by 2 divided by n by 2 multiplied by, right? So that's our final expression. So now let's calculate the limits. Okay. Let me see if I have it correctly. Yeah. So n is equal to 4 minus epsilon. N by 2 minus 2 is actually minus epsilon by 2. And n by 2 is 2 minus epsilon by 2. Those are the things which are here. And this one, 1 minus n by 2 is minus 1 plus epsilon by 2. So again, inside this gamma function, this also diverges, you can see. Okay. Now you use I'll write it once again. So this is 1 by 32 pi square So I will write this m square n by 2 as n by 2 minus 2 multiplied by m4, and I'll take this n by 2 minus 2 inside this bracket here. So I'll do this step here. So I'll put this m square here. Okay. And then I will use the fact that my n by 2 was what? N by 2 was 2 minus epsilon by 2, and n by 2 minus 2 was so this is the guy we have to calculate in the epsilon going to 0 limit. Okay. Then I use a few identities which you can again look up in Rider. He has shown it or any other place. So this has to have a pole when epsilon goes to 0. This is epsilon by 2. This guy is minus 2 upon epsilon plus 1 minus gamma I. This thing is this Euler-Mascheroni function close to 0.5. Okay. Then you also should expand. So what we are doing is we expand this whole thing in powers of epsilon, okay, and then look for poles of epsilon, then constant, then powers of epsilon square, epsilon square, and so on, which we in the end we can tend to 0. The epsilon powers, the ones which in the numerator will go away. So we will have either the poles or constant terms which we will keep. Okay. So again this 2 by 1 by 2 upon epsilon. So this I will write. This I will write as half. Okay. And the non-trivial thing I will do here, which is this is something to the power of a small number, epsilon. So I have something x to the minus epsilon. Okay. This I will write as, so I want to simplify this guy. This guy can be written as a log as follows. This is e to the power minus, log x to the minus epsilon, which is e to the power minus epsilon log x. Epsilon being small, you can write it as minus epsilon log x. Okay, expanding this exponential. So, where was I? We had this m square upon 4 pi mu square this will be 1 minus, here instead of epsilon we have epsilon by 2 log of m square upon 4 pi mu square. Okay. So now put all these things together in this expression and collect power, 0th power, 1 by epsilon power and so on. I think I'll stop at this point and continue. Just do one more step and I'll continue later. So this is giving us V phi, which is m4 divided by 64 pi square. Okay. So this another power of half came from this factor here. Okay. And you had a 1, and when you take this power inside, epsilon by 4, you will get one term which will be 3/2. You will see. So this one will multiply that and give you a half. Okay, when you take this inside that, this will multiply, this epsilons will cancel and you will get a power half. So you will get a term which is 3/2. Okay, and then some constant term. So let me write down and then you can. So this is 2 by epsilon minus gamma e plus log, I think 4 pi or pi. I think 4 pi. These are constant terms which will be thrown away, minus that 3 by 2 which I had log of m square upon mu square. So I guess this must be 4 pi. Okay. So now I'll explain next time little slower that you can, in the renormalization, what happens is you have that, so you have a classical Lagrangian, then you do one loop corrections, okay, but you also have a counter term, and let me call this as a bare Lagrangian. Okay, so this will give you the L0 plus delta L, one loop, there will be a counter term. So the job of the counter term is to have the same factors which will cancel out the divergences here. Okay, so basically in practical this thing, it means you just throw away the divergences and the constants you don't want, but it has a little more practical value which I'll show you, that this also gives you how the lambda renormalization. So if I throw away, I'll show this detail next. So the final answer for this is V1 loop is m4 upon 64 pi square log m square by mu square minus 3 half. And this is what's called the Coleman-Weinberg. One loop potential. And this m is actually, m square is d square v upon d phi square, right? The second derivative. So if you have a theory where L0 is half m square phi square minus plus lambda to the 4 factorial phi 4, then, so this is m effective, let's me call it. M effective square will be just the classical m square plus lambda by 2 phi square. So this is what you should put here. So I should actually start calling this m effective. M effective means second derivative of the potential. Okay. So now what you do is you put this back here. You will see that this is actually a function of phi, and I should call this now the phi b, because this is the classical Lagrangian. Okay. So this is your one loop potential. Okay. And this depends upon the renormalization parameter, but so does these constants, and overall if you write the renormalization of everything, then this mu square dependence goes away, which means that the mu square dependence of this potential cancels with the mu square dependence on lambda. So this is actually invariant under change of mu square. Okay. So all that. Okay, so now that I have the basic structure, it will be very simple to do fermion. Fermion loops will give you a minus sign, the same formula, okay, with a minus sign. So I'll show you how that comes. That's simple. And gauge bosons will give you the same thing with a factor of 3, because each gauge boson has 3 degrees of freedom. Okay, so that is, I'll leave that. I'll just assume that. So this is your 0th order potential. I'll just explain renormalization barely, not too, and fermions, gauge bosons, and then it is just one step away to convert this into the finite temperature. So this at finite temperature. So this I'll do next time. Thank you. Okay, I'm still a bit late. All right. Sorry. This was, I thought if I leave this midway, then it's going to get too complicated. Okay, thank you. All right. So